Okay, the work we're doing for this last homework set is direct derivations. Now in class I explained how we go from the concept of logical implication to apply that to arguments. That would be exercise set 3C. We're skipping that. Okay, we're not working on it, but I explained it in class, so I'm not going to belabor it here on the videos. It's going to be a theme too. Just try and make this efficient in these videos, get practice, but not belabor things I went over on Wednesday. Direct derivations takes this idea of logical implication, right? And applies it to argument. Okay, so let's look at a simple argument. P or Q, not P, therefore Q. Okay, the slash will be our sign for conclusion. P or Q, not P, therefore Q. P or Q. One of these is true, but P is false. It follows that Q is true. Okay. These two premises together logically imply the conclusion. If both premises are true, the conclusion has to be true. Look, if P is false, right? You have two premises, we'll number them, right? Premise 2 says P is false. Okay? So in order both premises to be true, when P is false, you see how, right? You have to keep P constant. We're in a scenario where P is false, but both premises are true, right? Well, it has to be that Q is true in order for this statement to be true. Okay? This is called a shortcut test. That's quick. That's the idea. The two premises together imply the conclusion, right? Anytime both these premises are true, this is true. And you could test that with the truth table. You could test that with a truth table. These premises are both, the premises of the argument are both true only in this row, and the conclusion is also true. Anytime the premises are both true, the conclusion is true. Then that's it for validity. Remember chapter 1? You don't need to have a false conclusion every time you have false premise, blah, blah, blah. A valid argument means anytime the premises are true, the conclusion has to be true. Okay? And now, we learned back in chapter 1 that validity is based on form. These statements logically imply the conclusion because of this structure. One of these is true, but this is false, so this is true. So this pattern applies for more complex arguments. Either the Mets and the Dodgers make the playoffs, or the Phillies and Cubs make the playoffs. It's not true that the Mets and Dodgers both made the playoffs, right? One of them didn't, right? Not both. Therefore, the Phillies and Cubs did. Okay? You still have your P or Q, not P, therefore Q structure. Okay? These P's and Q's, this pattern works for any, P can be any proposition as long as you keep it consistent here. Q can be any proposition as long as you can keep it consistent here. All right. That's what we're working on here. How do we do direct derivations? When we're giving, we can use direct derivations to show that arguments are valid when it would be too cumbersome to do it with truth tables, that's kind of the idea here. You can get 4 or 5 premise arguments, and it would be annoying to try and show in truth tables. You need 32 rows. Sometimes, but actually they have a pretty simple structure that you can break down and show the argument to be valid. So what are we looking at with these direct derivations? We're looking at valid argument patterns. Valid argument patterns, okay? And we have just 3, okay? We're doing simple derivations. I think he calls them simple derivations, I think about it. Simple derivations, I call them direct derivations. Simple derivations. You have 3 patterns, okay, that you have to learn. But you have to be able to recognize those patterns, right, in any argument, okay? you have to recognize P arrow Q is a pattern, but when P and Q can stand for any proposition, right, this premise is an arrow proposition just like this. So here's one of our patterns, P arrow Q, P therefore Q. Okay. So this is our very general pattern where P and Q can stand for any proposition, right? And in a particular argument, you have to be consistent. Q here has to be Q here, P here has to be P here. But that doesn't have to be simply a capital letter. P can be a conjunction. A and B implies C, and A and B are both true, therefore C is true. Okay. With that in mind, let's talk about our three patterns. We have two arrow patterns and an OR pattern. Okay. First pattern, P arrow Q, P therefore Q. This is a very general pattern that says when you have a premise with the arrow as the main connector and another premise that says the antecedent is true, you can deduce that the consequent is true. Okay, you can deduce that the consequent is true. This is pattern one. With this pattern as a name, it's modus ponens. We abbreviated MP. And I'm just going to talk about the patterns, and then we'll talk about applying the pattern to argument in another video. Okay, next pattern, also an arrow pattern. Okay, two premises, two premise pattern. All these argument patterns are going to be two premise patterns, and when I practice exercises, I'll show what that means. Also, you start with an arrow statement, any arrow statement. Okay. The second premise, the other premise says the consequent is false. It denies the consequent. You need that negate, right? Here you had drag and drop. Here you have negate. Okay. If the consequent is false, it follows that the antecedent is false. You cannot go the other, so this is called modus tollens, right? You don't want to do this, P arrow Q, not P, therefore not Q. That's invalid, right? If Ann is here, then Bob is here. Ann's not here, therefore Bob is here is a bad argument. Very bad argument. Okay, right? If Ann is here, then Bob is here. Ann is here, therefore Bob is here. But remember, this also applies to the pattern. If Ann and Bob are here, then Carl is here. Ann and Bob are here, therefore Carl is here, right? P can be any proposition, simple or compound. If Ann is here, then Bob is here. Bob's not, so Ann is. That's your modus tollens pattern, okay? Your other pattern is an either or pattern, P or Q, any either or proposition. And then half of it is false, so the other half is true. Now we give you two patterns here, right? There's two ways to do this. The left half is false, so the right half is true. The name for the pattern is MTP, related to MT. It's also called disjunctive syllogism, a two-premise argument using a disjunction, but for our book, we call it MTP, for our abbreviations. We have MP, modus ponens, MT, modus tollens, MTP, which is our disjunction argument. This half is false, so this half is true. Now notice we said the left half was false, so the right half is true. It turns out that Q or P is equivalent, right, to this, right? And if we had gone further with these derivations, logical equivalence, which we discussed the last chapter, would loom larger in these derivations. But we give you kind of a shortcut here, recognizing that to say, well, this is pretty much the same, not Q, therefore P. The left half, the right half is false, therefore the left half is true. And we just call this MTP2. And I'm not going to be fussy over whether you remember MTP1 or 2. If you identify the rule as MTP1, as MTP, you'll be in good shape. Now, how do we use these rules? We use these rules to recognize patterns in arguments. We use this to recognize patterns in arguments. These are our three rules that allow us to draw inferences from premises that we're going to give you. There are other rules we could give you, but these are the three we're going to allow you to use to keep things keep things straightforward and simple. So I'm going to give you a quick example here. Okay, it's going to be quick and straightforward, and I'm not going to explain. I'll go into explaining more what we're doing in a subsequent video, but just so you can see the idea of these patterns. Here's an argument. I'll use it with A's and B's to remember that P's and Q's can stand for anything. Either Ann or Bob is here. Bob is here, then Carl is here. Ann's not here. Okay. You have 3, right? So you need 8 rows. This is 3 premises. This would be complicated to test with truth tables. But hopefully you can see already what follows. You can deduce C, that Carl is here, from these 3 premises. These 3 premises logically imply the conclusion C. If anytime all these 3 premises are true, so is C. Okay? How are we going to get there? Well, we can recognize some of the patterns we've already seen, right? And notice intuitively reasoning with this, we would do the same thing you're going to do in these derivations. Well, if Ann or Bob is here, but Ann's not, it has to be that Bob is, right? So we mark down that inference as a new row, a new line, okay? And then we're going to tell what rule we used. Indeed, we used the MTP rule, and we based it on premises 1 and 3. Premises 1 and 3 together follow the MTP pattern. Since Ann or Bob is here, but Ann's not, it follows that Bob is. Now we can use this. We've drawn this valid inference from these premises. So now we can reason further using B and these other premises. And since Bob is here, and if Bob is here, then Carl is here, it follows that Carl is here, right? By B arrow C and B. Since B arrow C is true and B is also true, it follows that C is true by 2 and 4, and that's our modus ponens pattern. Okay, and I'll explain more what we're doing here in this inferences, right? But you took 2 steps using pattern recognition to derive the conclusion of the argument from the initial premises. And that is derivation. You show that you can infer validly the conclusion from the original premises using these patterns. Okay? Talk some more about that.